from the University of Salento, and he will tell us about the Hamiltonian structures of WDVV-type. Raf, you're welcome. Please begin.
Okay, thank you very much, Joseph, and I thank you very much for giving me the opportunity to speak at a seminar. It's always a pleasure. And so today I will speak about certain class of Bi-Hamiltonian structures, which we call the WDVV type. The work is in collaboration with Stanislav Opanasenko, who is research fellow at the INFN, so National Institute of Nuclear Physics at my university. Okay, so let me describe briefly what are the contents of the talk. We will speak about Bi-Hamiltonian systems of PDEs, but in particular of the WDVV type class, which is a kind of a special case of KDV type. And then after describing the class, we should say something about how do we find systems in this class. And for this reason, we need to, in order to solve this problem, we need to find the equations for compatible pairs of operators. This is a non-trivial task for the class that we considered. And there is a work in progress, which is almost finished, and we hope to put it in archive soon. And in the end, I will describe low-dimensional classification and many examples from the class that we are considering. This has already been published, but it will be improved a lot once our preprint will appear in archive. Okay, so we consider evolution equations with an arbitrary number of unknown functions of two independent variables, so functions of t and x. And we will consider systems of the following form. The Bi-Hamiltonian pair is made by a linear combination of many operators, many different operators, and such operators are homogeneous with respect to x derivative. So this means that they are, if you sum up all its derivatives appearing in the expression of the operator, you always have the same number. But the sum of operators of different homogeneity degree is what happens a lot of times in concrete examples. So in particular, we can consider the expansion of P as P1 plus epsilon S2 plus epsilon square S3 and so on. And Q as Q1 plus epsilon R2 plus epsilon squared R3 and so on. Where P1 is an operator of homogeneity degree 1, S2 is an operator of homogeneity degree 2, and so on. The same for Q1, R2, and so on. In concrete example, we see a lot of times that a Bi-Hamiltonian pair is a pair of two Hamiltonian operators, where one is, for example, of first homogeneity degree, and the other has mixed homogeneity degree, and it is indeed the sum of two different operators of different homogeneity degrees. In many cases, the second operator is the sum of one operator of first homogeneity degree and an operator of second or third homogeneity degree. So this is the normal situation. Sorry, here there is a misprint. It should be epsilon to the square. for us, it's not very important, this epsilon. Anyway, what we would like to discuss today is that there are many systems where the Bi-Hamiltonian pair is not of this form. So it does not have in one of the components, in one of the members of the pair, the first order part or first homogeneity degree. So this means that we have a pair of operators, one of first order, another of third order, for example. We have many examples of, say, well-known partial differential equations which have pairs of this type. The majority of examples comes from WDVV systems. WDVV equations can be rearranged into systems, evolutionary systems, which possess exactly this kind of Bi-Hamiltonian pair. So this is what we would like to discuss. A kind of singular class in the set of all integrable systems. It is singular in the following sense. Let us have a deeper look at how many examples we have in the case of compatible triples of Hamiltonian operators and compatible pairs of Hamiltonian operators. When we have compatible triples, we have a host of examples, like, for example, the Korteweg-de Vries equation, Kamasa-Holm, dispersive water wave systems, coupled Harry-Dean, and so on. This with third-order operators. With second-order operators, we still have many examples, AKNS, two-component, Kamasa-Holm, Kaup-Brewer, and so on. The situation changes quite drastically when we consider compatible pairs, because we have as main examples in two components Monge-Ampère equations, in three components, from three components onwards, WDVV equations, and oriented associativity equation. With second-order operators, we have no known examples. At least I do not know any example in literature where the Bi-Hamiltonian pair is made by second-order homogeneous operator and the first-order local or non-local homogeneous operator. So again, this is the main reason why, coming back to the previous slide, we will focus on systems of the form where the Bi-Hamiltonian pair is of the form of one operator of the first order, homogeneous, and another operator of the third order, again homogeneous. We do not consider the second order case, not because it's not doable, the computation or the examples. I am sure that one could find a lot of examples. The point is that, at least as far as I know, there are no systems in literature with this pair of operators. So let us have a look at the KDV example, just to clarify the ideas. So if we consider KDV equation, it's an evolutionary equation, it is scalar. It has a Bi-Hamiltonian pair, A1 and A2, which is made by three Hamiltonian operators. There is a first-order operator P1, a first-order operator Q1, and a third-order operator B cube X. They can be combined in two different ways, because you can move D cube X from Q1 to P1 and the other way around. So if you assemble A2 as Q1 plus epsilon square R3, you obtain the standard Bi-Hamiltonian pair of the KDV. And this A2 is just the Magri Hamiltonian operator. And then you can move R3 to P1, to sum, you can sum it to P1. And in this way, one can obtain the pencil that defines the Kamasa-Holm hierarchy. So this is, how to say, it doesn't exhaust all possible integrable Bi-Hamiltonian systems. There are many Bi-Hamiltonian systems which are Bi-Hamiltonian with respect to different arrangements or different combinations of homogeneous or non-homogeneous operators. But many famous equations fall into this class. So we call such equations equations of KdV type. We studied it in a couple of papers, together with Salvoldi and Lorenzoni, and later with Lorenzoni. So now let us rehearse what do we mean by Hamiltonian PD. Hamiltonian PD is a system of evolutionary equations where the right-hand side, where the left-hand side is of course the time derivative of the field variable. The right-hand side can be expressed through a Hamiltonian operator and a Hamiltonian density. So we apply the Hamiltonian operator to the variational derivative of the Hamiltonian density, and we obtain the right-hand side of the system. Now, what we require to the Hamiltonian operator is further property, because we would like it to define a Poisson bracket, as every reasonable Hamiltonian formalism should have. And the Poisson bracket is defined by the expression on top of the slide. It uses variational derivatives of functionals, and it uses the operator applied to one of the two variational derivatives. This is not really important in the sense that due to the fact that we require further properties, and in particular skew adjointness to the operator, in such a way that the Poisson bracket be skew symmetric. This is very important. And we would like also that the Poisson bracket fulfills the Jacobi identity. And this amounts at a requirement on the operator, which is just the fact that the variational Schouten bracket vanishes. The variational Schouten bracket is a nonlinear expression made by the operator, and it is not so difficult, even if it can be a long computation, to verify that a certain operator is Hamiltonian, while it is not so easy, generally speaking, to find Hamiltonian operators for a certain PD. Then we will consider homogeneous operators. They were introduced by Dubrovin and Novikov many years ago, and they are form invariant under point transformations of the dependent variable. This means that they have a differential geometric content. Indeed, if one considers the first order local case, we have a homogeneous operator of degree 1, which has a derivative dx, which is multiplied by a coefficient matrix, plus a derivative ukx, which is multiplied by an indexed family of functions. Of course, such an operator must fulfill the requirements that we discussed before, so it should be skew adjoint, plus its Schouten bracket with itself should be 0, and this leads to a series of conditions that we will see in the next page. There is a non-local generalization that, to the aim of this talk, is quite important, and it was it started with joint work with Moch and Genia Ferpontov, but then Genia continued to a more general form of such non-local operators, and we need essentially this more general form, because this is what happens in WDVV equations in general. So you cannot do anything more simple than this. And you may notice the fact that there is a non-local tail. This non-local tail of the operator is a linear combination of non-local parts, and the coefficients are arranged into a constant symmetric matrix, which is denoted by C alpha beta in this slide. Okay, so what are the main differential geometry properties of these first-order operators? So after a point transformation, the leading coefficient matrix Gij transforms as a contravariant to tensor. We always work in the non-degenerate case, so the leading coefficient matrices are non-degenerate, determinant different from zero. Then with this invertible matrix, we can lower and raise the indices, and then we prove that there is a connection, a linear connection hidden into the operator indeed, embedded into the operator. And let us see what are the properties of the coefficients of these operators. Basically, square jointness and Jacobi identity give two different sets of properties. Square jointness implies the symmetry of Gij, and also another condition on the derivatives of Gij in upper indices. And then the Jacobi identity implies other conditions. And the first one, which is listed here together with the previous ones, implies that G, the leading coefficient matrix, behaves like a pseudo-Riemannian metric, and okay, the inverse of a pseudo-Riemannian metric. And this metric is the Levi-Civita, sorry, not exactly. The metric, the connection gamma, which is embedded into the operator, is metric with respect to the metric G. But then the Jacobi identity also implies the symmetry of this connection, and this means that gamma is really the Levi-Civita connection of G, so it's uniquely determined. So the whole operator is determined by G, the first order operator. This is not true if the operator is non-local. If the operator is non-local, you also need the W part, the non-local tail. It should be given. And the conditions that the non-local part should fulfill are listed below. So there is a condition on curvature in particular, which when the operator is local, implies the flatness of the Levi-Civita connection. So the metric must be flat, but this is not always the case, because we will encounter many examples of non-flat metrics in what follows. Higher order homogeneous operators. Here we consider second order and third order homogeneous operators. They are second order and third order, but they are also second homogeneity degree and third homogeneity degree, in the sense that the number of x derivatives that appear in the expression of the operators in every summand is always the same, 2 in the first case and 3 in the second case. So the expression is very complicated, this expression, but you never look for operators in this form, or for higher order operators in this form. You look for higher order operators in a simplified form, which can be achieved once one observes that, okay, in the non-degenerate case, you have two connections hidden into the operators. Again, the point is that this time these connections are not metric. So there is no strict correlation between these connections and the leading coefficient matrix of the operators. But it can be proved, it was proved by a PhD student of Novikov, Potyomin, and independently by Doyle, a PhD student of Peter Holder, that these connections are flat, and then hence one can use flat coordinates. In flat coordinates, it can be proved, so they are not only flat, they are also symmetric. In flat coordinates, it can be proved that the expression of the higher order operator simplifies a lot. And moreover, there is a lot of projective geometry in these operators. So we will use this simplified form, because in this simplified form, we can use a classification which was found starting from many years ago with a working collaboration with Jennifer Apontov and Maxime Pavel, several papers. But I stop here speaking about second-order operators. I will focus on third-order operators because, as I told you, they happen in examples. Third-order operators in the simplified form. The Hamiltonian property is relatively simple. So basically, the leading coefficient matrix determines everything, exactly as in the first-order case. The point is that the interesting fact is that third-order operators are determined by what is called the Monge metric. So there is an algebraic variety which is called quadratic line complex, which is attached to every Monge metric. It can be expressed by means of a Monge metric. But this talk is not about this kind of properties of the operators. So let us have a look at what I consider one of the two most inspiring examples for this talk, which is the WDVV equation. WDVV comes from Witt and Dijkgraaf, Verlinde, who discovered this equation in the context of string theory. But later it was observed that this equation has very strong connections with the theory of integrable systems, because basically its solutions represent for every solution you have a Bi-Hamiltonian pair of local operators of the first order. So basically this equation is an equation whose solutions correspond to integrable systems, at least in certain particular context, under certain hypotheses that I do not want to discuss here. So a trick which was, I think, first introduced by Mohoff, but then exploited by Mohoff and Jennifer Apontov, is to introduce some new variables, and then which are u1 equals to fxxx, so u2 fxxt, u3 fxtt. So you select one independent variable and consider all derivative coordinates which contain at least one derivative with respect to that selected, which is x in this case, independent variable. And then you consider all the compatibility conditions, so cross derivatives basically of these variables. And you come to evolutionary systems. And this is the prototype evolutionary system which corresponds to the simplest associativity equation. And for this system, we have a clear notion of what is a Hamiltonian system and how to look for Hamiltonian operators and so on. In this particular case, it was found by Jennifer Apontov, Falek Mohoff, and others, and Mutku and Galvon, that this system has a Bi-Hamiltonian formalism exactly with two operators. One is a local first-order homogeneous operator, and the other is a third-order local homogeneous operator, exactly of the types that we discussed now. In particular, the third-order operator is in simplified form. It has the x and the x factorized in the beginning and in the end. And in the middle, there is a first-order operator. So the idea is, does there exist any other system of that type? So are there any other systems of conservation laws of the same type, which have a Bi-Hamiltonian pair of the same type as WDVV? Of course, when we are speaking about Hamiltonian formalism for WDVV, we are speaking of Hamiltonian formalism of WDVV in the form of a first-order system of conservation laws, exactly as we have seen 2 slides before here in the square, red square in the bottom. We consider Bi-Hamiltonian pairs made by a first-order homogeneous operator of Raffaele type. This is important because a local operator would not suffice, would not be enough, because in concrete examples, in WDVV equations, you happen to find non-local operators. So the non-local case must be considered. And a third-order homogeneous operator in canonical form. So why to take them in canonical form? Because there is a clear classification of operators in this form. So we can use that classification to find compatible first-order operators and then systems. Let us speak about the compatibility conditions. Now, finding compatibility conditions P1 against R3. So the Schouten bracket, this means compatible operator, must vanish of the operators P1 and R3. This is quite a hard computation. Recently, we have been able to finish it, and we hope to post the paper in archive as soon as possible. And among the main results in this paper are the fact that the compatibility conditions have been integrated to algebraic equations. So we have got rid of all differential equations. They are completely solved. And the set of residual conditions are algebraic equations, which hence are just the intersection of some algebraic varieties. And for this reason, the family of operators P1 R3 is parameterized by a finite number of constants once you fix one of the two. And the non-local part of P1, so let me be more precise. Let us come back for a moment to the expression. So the non-local part is in the bottom rectangle, the part whose coefficient is C alpha beta. So this Wi alpha k uk x, they can be considered as right-hand sides of first-order quasi-linear systems of PDEs, of evolutionary systems. And indeed, one could prove that they are total derivatives. So these systems are conservation laws. This is a result of compatibility computation. And the fact that those systems are Hamiltonian systems with respect to the third-order operator. So again, the non-local part of P1 is made by Hamiltonian systems of R3, of the third-order operator. In previous works, we found that such Hamiltonian operators were already computed up to linear algebraic equations. So again, we had some conditions which were differential in principle, but we were able to solve all of them and to find linear algebraic equations that determine Hamiltonian systems of a third-order operator. This, of course, is in line with the previous statement, the fact that compatibility conditions have been integrated to algebraic equations. And then another feature is important. We have a structure formula, and it is more precise than what I'm writing here. And it has been proved that the metric of the first-order operator is completely determined by a square matrix of quadratic functions of the field variables. And this makes finding compatible first-order operators quite possible. Unfortunately, one negative surprise was the fact that the leading coefficient matrices G1 and G3 of the two operators P1 and R3, they do not make an endomorphism with vanishing Nine-Hoist tensor. So we cannot see any Nine-Hoist geometry in this kind of computation. Of course, if you have two operators of the first order which are compatible with an operator of the third order, you can check the compatibility between those operators, first-order operators, and that depends also on the vanishing of the nine-noise tensor. But this is not under consideration here. So then we start speaking about the affine classification of the third-order operators in two components. So we now, in the rest of the talk, we will speak about classification or examples in different dimensions. We start, of course, from the lower dimension. In n equals 1, there is nothing. Nothing non-trivial. So in n equals 2, there is something, relatively few, you will see. Basically, if we fix the operators in this classification, this is an affine classification, then we fix the higher order operator, and then we try to determine all compatible first order non-local operators. And then what we find is what you will see. I'm just saying that we will discard R1 because systems which are Hamiltonian with the constant coefficient operators are not interesting, as they are linear. So they are outside consideration here. Well, for now, we consider R2. R2 is the second operator here. You can see that it's non-trivial. And R2 is the Hamiltonian operator of a family of systems. In this family, we are going to see what are the Hamiltonian systems with respect to a possibly non-local Hamiltonian operator of the first order. And we find that all of these systems are Hamiltonian with respect to three first-order operators, which are even local, and they are listed below. Okay, and then we can consider R3, and again, we have the same situation, basically. So we have that such systems are the Hamiltonian systems of the third-order operators are also Hamiltonian with respect to three different compatible operators of the first order. It should be said that they are compatible, all the three, with the third-order operator, but they are also compatible between themselves. So they constitute first-order pairs for such systems. And indeed, some of the systems were already known in the literature in one form or in the other, but the Hamiltonian structure that was known was mostly the first-order structure, because since they are Bi-Hamiltonian by first-order operators, who cares about higher-order operators? So we can also attempt a projective classification. How to do a projective classification? Well, if we consider projective transformations, we destroy of the dependent variables, we destroy the flat coordinates structure that I was telling before. The point is that if you modify the projective transformation of the dependent variables by adding a non-local transformation of the independent variable, what you see here, dx tilde is equal to delta dx, where delta is the denominator of the projective transformation. This is called a reciprocal projective transformation, and this transformation preserves the canonical form of the third-order operator. So this means that we can use the classification of higher-order operators based on projective reciprocal transformations. Well, in this low-dimensional case, there is only one case of such one instance of operators, because all the three operators, these three third-order operators, collapse to R1 under reciprocal projective transformation. So it's not very interesting. But let me discuss a couple of well-known examples, which are, first of all, the Chaplygin gas system. The Chaplygin gas system is known to admit three first-order local Hamiltonian operators. then one could think that it is of our type, and indeed it is. It can be diagonalized as the system that you can see. It should be said that all Hamiltonian systems, which are Hamiltonian with respect to a third-order operator, are also linearly degenerate, and this is the only linearly degenerate system in 2 dimensions. But what happens is that it is clear that the diagonalizing transformation does not change the form of the 3 first-order operators. What is less clear is that a Chaplygin gas system has a third-order homogeneous operator. This diagonalized system has a third-order homogeneous Hamiltonian operator. The point is that these operators are not in canonical forms, so it's difficult to express them. But the point is that this diagonalized system can be transformed into the next equation that you will see. So this equation is, well, we have an equation and the system. The equation can be made into the system with a similar mechanism. It's exactly the same as we have seen for WDVV. And what happens is that this system can transform into the Chaplygin gas by a nonlinear transformation. But this system has a third-order operator exactly in the same, in the canonical form, and in particular, it is the operator of the operator R2 that we have already seen. And this was known in literature. So basically, all these known examples can be transformed one into another, and but this destroys the canonical form of the operator R3. We can pass to 3 components. Here, things are a bit less, how to say, known. In particular, so we consider systems of conservation laws. Again, an operator in canonical form of the third order. You see the X is factorized, one before, one later, one after. And it must be said that all the leading coefficient matrices of an operator of this type, Hamiltonian operator of this type, can be factorized. Can be factorized in the following form, last equation of the page, of the slide. So we have phi alpha beta, which is a constant symmetric matrix, non-degenerate. And then we have psi alpha I, which is a matrix of linear functions, and psi beta j the same. So it's basically the square of 2 matrices of linear functions, which fulfill certain equations which define Hamiltonian operators. We will use this splitting because it can be proved that the compatible Fedorov operator of the first order, compatible with the third order one, in low dimensions, has the form which I wrote here. So the local part is what you expect, and then you have 3 non-local different bits, summands, which are each multiplied by coefficients C11, C12, C22. And the metric or the leading coefficient matrix of the operator has the form which I write here, psi I alpha, q alpha beta, psi j beta. In our previous paper with Stanislav Opanasenko, this was a conjecture. But now in our recent research work, still unpublished, we will put in archive, it is proved that all the compatible metrics of the first order operators have this form. And q alpha beta is a quadratic function. And it could even be proved that q alpha beta has a more detailed structure, which involves Hamiltonian systems of the third order operator, which are the key to everything. So after this discussion, we consider the classification of Monge metrics which give rise to third order operators. This is a fruit of research work by Jennifer Apondov, Maxim Pavlov, and myself in 2014. We proved that there are essentially these 6 cases. And now let us go case by case. So if we consider R6, you see that it is a constant coefficient matrix, not very interesting. Linear systems, we do not consider them. R5, the WDVV equation, which is our prototype, and this has been found very many years ago by Jennifer Vodo, Alek Mokhov, and Yavuz Nutku and Galvon in 98, I think. So then R4. This R4 was already known in literature, and for a WDVV Bi-Hamiltonian system, and it was found, the Bi-Hamiltonian pair, by Nutku and Kalaichi. And again, this Bi-Hamiltonian pair was local, like in the previous case. But then here we started to find new things. So we considered another Bi-Hamiltonian system. This is again WDVV. But it is WDVV from a class which was not, how to say, not considered so much by Dubrovin. He speaks about this class just in the very beginning of his long paper, Geometry of 2D Quantum Field Theory. This system was considered by Agafonov in 98, and then by same triple of people after many years, and then by Jakub Vasicek and myself in 2021, when we found out that this system admits a non-local first-order operator Farapontov type plus a third-order operator in canonical form. And here you see all the data. Basically, with this simple data, we can reconstruct the operator, which has, of course, a much more complicated expression. It is easy to write down this data. It is much more difficult to write down the complete form of the operator. Well, in this case, it's still possible. But when you go to these cases, to the case of R2, we have a Hamiltonian system of the operator R2, and complicated expression of the matrix Q of quadratic functions, plus non-local tail, which you see the non-zero coefficient in the non-local tail, this and this. And the two bottom matrices, the two matrices, the bottom line are just the factors of the Monge metric of the third order operator. And then we have R1, for which we have similar situation. So we have a Hamiltonian system with respect to R1, and then we can assemble the first order operator using these constants. You see that they are all non-zero in general, plus the matrix Q, which is here, plus the factors of the decomposition of the Monge metric of the third order operator. Now, let us consider a full projective classification. What is a full projective classification? We proved so far that if you exchange T and X, and then you append another projective transformation, you can enlarge the projective group acting on the operators. And the full transformations involve also dt, and they can be written in the following extended way. Under the action of this group, there are only two equivalence classes. The number of equivalence classes reduces, it becomes much smaller. And they will be basically R5 and R6. So R6 is the constant coefficient operator, and R5 is the prototype WDVV equation. So nothing new indeed. Under the action of this big group. The point is that even when you know that the equivalence classes are very small, how to say, are very big, they are just two, how to recognize the transformation that brings one member of this class into the canonical form, this is very, very difficult. The methods that we gave in our paper made it possible to compute the Bi-Hamiltonian pair without too much pain. While even if a priori it is known the membership into a particular class, finding the operators exactly in that form, so find the change of coordinates that brings you in that form, would be an impossible task, basically. So n equals 4, this is interesting because for the moment, until n equals 3, we found all integrable systems. In n equals 4, what happens is that we have a kind of big classification of third-order operators, but even when we consider simple generalization of systems that we have seen in 3 components, such systems do not admit any compatible first-order operator. So they admit a third-order operator, for example, a system of the form 1, it is called a reducible system. They have been studied by Agafonov again. But in 4 components, there are only 2 cases of such systems when they admit a third-order operator for the functions in displayed equation number 2, the 2 functions f1 and f2, and we can prove that in none of these cases admit a compatible first-order operator, and we do not even know if such systems are integrable, and indeed they fail a test about the number of conserved quantities that they should have in order to be integrable. So it's unlikely that such systems, although Hamiltonian, are integrable. But this is a kind of no-go example. So it's not true that if you take a Hamiltonian system with respect to a third-order operator, it will be automatically integrable, at least in Bi-Hamiltonian sense, in this category. So, but let us see one integrable example. It is conjectured by Jennifer-Abodov that there is a unique such example in 4 components. And this is this system, the system of PDEs that you see here. This system has a particular geometric meaning that you can find in probably one of his papers, and also another paper which was written also in collaboration with Maxim Pavlov and myself. So this system has a Bi-Hamiltonian pair. This is the Monge metric that determines the third-order operator. This was already known in 2018. Together with Stanislav Opanasenko, we found out that the system admits, so the psi and phi are the decomposition of the Monge metrics, the factors. With Stanislav, we found out that this system has a non-local first-order Hamiltonian operator, which is defined by these parameters, and C11 and C12 are just 1, while C12 and C21 are 0. So, but there is a non-local tail. And then let us see what is the situation in n equals 6. I'm almost finished. So with Maxim Pavlov, we proved that there is a common Bi-Hamiltonian pair of WDVV type for 2 commuting first-order quasi-linear systems of PDEs, which are obtained from WDVV equations in dimension capital N equals 4. Capital N is not the number of components. Here we have capital N is a dimension which is characteristic of WDVV. When you transform the WDVV equations in quasi-linear systems of the first order, you introduce a lot of variables, and then it turns out that the number of components is 6 for such first-order systems. So we go from 4 to 6. There is nothing, we didn't find examples, known examples in the middle. this is a result that we found many years ago. But then what we found is that together with Stanislav, we observed that there were six component systems of the first order, systems of conservation laws, which were related with integrable Lagrangians of this form, depending on second order derivatives only. And the paper is a paper by Zhenya, Maxim Pavlov, and Ling Shui. It is an archive. So we have been able to find a common Bi-Hamiltonian pair, again in 6 components, for two commuting. So two commuting first-order quasi-linear systems, the same Bi-Hamiltonian pair. And again, we proved, and we hope to publish these results in archive soon, that WDVV equations in all dimensions, once rewritten as n-2 commuting systems of first-order PDEs, admit a third-order Hamiltonian operator in canonical form. And only when n equals 4, we have been able to prove that the systems are Bi-Hamiltonian of WDVV type. So this covers all WDVV systems in dimension WDVV dimension 4, not just the particular example that we dealt with Maxim Pavlov many years ago. Again, we have to post this paper in archive. So final remarks, we recall that we have a Bi-Hamiltonian pencil of this form where we have the red factor and the blue factor. Sorry, not exactly summand. Yes, summand. If we consider extended sums starting in both cases from first order terms, this is how Dubrovin and Zhang approached the classification of integrable Bi-Hamiltonian systems. It is a perturbative approach. It is inspired by finite dimensional classification, well, finite dimensional analysis. But they always assumed that Q1 and P1 are non-zero, so they exist and they are perturbed. While we are in a completely different situations with these WDVV systems, they are somehow singular because the pencil starts in one of the two instances from a higher order operator. This kind of situation can be extended also to the left, because one could introduce 0-degree operators. So consider the sum of 0 plus first-degree operators. And this is studied, this was studied recently. It was well, such a study was introduced many years ago by Mohoff and others. Recently, it has been continued by other people, Delatti, Oliveri, Rizzus, Groiger, Gallo. There are some papers in archive, but without direct application to the study of integrable hierarchies. Okay, and this means that why I am speaking about this, because in principle one could study Bi-Hamiltonian pencils of different shapes. So for example, we could use a second order operator instead of the third order operator, start from 0. We can do different things, or we can consider different ansatz, and instead of considering conservation laws of the previous form, which are first order systems, we could consider second order systems of conservation laws or third order systems of conservation laws. But then the point is, do we have examples that justify the effort of spending time on this particular problem? I don't know, maybe in some cases, yes. Okay, and that's all. Thank you very much.
Thank you, Raf. It was very interesting. Questions, remarks? Женя, Boris.
Give me a second. Can you hear me?
Yes,
Oh,
yes.
yes. Hi, Genia.
Oh, Raffaele. Hi, Raffaele. Thank you. I have a question. So, for general WDVV, am I
Yes.
right that you found a third order operator, but you still cannot prove that first order non-local operator also exists? You haven't proved yet. For
Not in general.
In
In
general.
n equals 4, yes, but not in general.
Even for next value of n, you can't check it. For n equals 5, can you check it?
At the moment, no. Maybe a computation can be done, but I do not have any general statement for the moment. We do not have any general statement for the moment.
Okay, yeah, I see. But you believe they exist, right?
I am 100% sure.
All right. Okay, thank you.
More questions, more remarks? Okay, Raf, I have a quite small question. What software did you use for computations?
Well, I use reduce, and when I have to compute brackets, I use reduce. But Stanislav uses Maple for other computations, sometimes also for brackets, yes.
Okay,
But
and
mostly Maple. Yeah. So, and by the way, and we check each other. When it's possible, we do the same computation with the two systems.
Yes, and a request, can you send us your slides?
Oh, of course.
Yeah, okay. Thanks a lot. So thank you very much for visiting this session, and next time
Thank you very much.
Thank you. And you will receive, we shall meet next time in May, and you will receive the corresponding notifications. Goodbye.
Bye-bye.